There is a number that almost completely destroys one of humanity's oldest fantasies. It is not a complicated equation. It is not a speculative theory. It is just a distance. 2.5 million light years. That is the separation between the Milky Way and Andromeda, the closest galaxy to our own. It might seem like an abstract number, but in reality, it is a sentence. Imagine this. If the Milky Way were a coin in the palm of your hand, Andromeda would be another coin placed 3 meters away. It seems reachable, but every millimeter between those two coins represents 1,000 light years of absolute vacuum, a space so hostile that neither life nor complex matter nor human time make any sense there. Our furthest spacecraft, Voyager 1, has been traveling non-stop for nearly half a century, and it hasn't even left the solar neighborhood. At that speed, reaching Andromeda wouldn't take centuries, nor millennia. It would take more time than humanity has existed as a species. And yet, distance is not the real problem, because even if we could travel faster, even if we mastered unimaginable energies, the universe itself would be working against us. Space expands, galaxies move away, and most of the cosmos has already crossed a point from which we will never be able to reach it again. So the question is no longer how to leave the Milky Way. It becomes something much more uncomfortable. What if we were never destined to do so? This is Impossible Horizon, and today we are going to explore why, no matter how much we advance, the Milky Way might be the ultimate limit for humanity. For decades, science fiction taught us an almost inevitable promise. First, we would colonize planets, then solar systems, and one day, we would leap between galaxies. It was just a matter of time, of progress, of technology. But physical reality doesn't work on promises, it works on limits. We are not facing a difficult challenge, we are facing an absolute wall. A set of laws that do not bend with ingenuity or hope, laws that do not distinguish between advanced or primitive civilizations. They simply exist. Today, we are not going to talk about impossible engines or magic portals. We are going to analyze something much more uncomfortable. The invisible bars of our cosmic cage: distance, energy, time, biology, the expansion of the universe. Factors that combined draw a conclusion that is rarely said out loud. We will likely never leave our galaxy. Not because we lack intelligence, not because we lack will, but because the universe itself might have drawn a perimeter around us from the very beginning. And understanding that perimeter is not a surrender. It is looking at the cosmos without fantasies and discovering what our place in it truly means. To understand the magnitude of the problem, one only needs to look at the human object that has traveled the furthest, the Voyager 1. It was launched in 1977. It has traveled non-stop for nearly half a century. It has left the solar system and moves at about 17 kilometers per second, a speed that on Earth would seem dizzying, and yet it has reached no star. If we pointed Voyager toward Proxima Centauri, the nearest star, it would take approximately 73,000 years to reach it. That means by the time it arrived, human history would have changed so many times that the very concept of nation or language might be unrecognizable. Now, let's take that calculation to Andromeda. We aren't talking about tens of thousands of years, we are talking about 1.8 billion years, a period so long that, according to stellar models, the Sun would have already increased its luminosity enough to evaporate Earth's oceans. In other words, our civilization would have disappeared long before the spacecraft completed the journey. And that is assuming the ship never failed, that no particle destroyed it, that energy was infinite, that time did not erode its materials. The distance between galaxies is not just large, it is inhuman.
It is not meant to be traveled by biological organisms or by machines that depend on maintenance. It is an abyss where time stops being a tool and becomes an enemy. Even before we talk about impossible engines or futuristic technologies, pure mathematics already tells us something powerful. With our current speeds, leaving the Milky Way is not a difficult mission. It is a timescale that exceeds the life of any civilization.
Let's assume for a moment that we solve the problem of time, that we manage to build a spacecraft capable of traveling much faster than Voyager. Then the next wall appears, one that doesn't depend on engineering, but on fundamental physics: energy. Accelerating an object in space isn't simply about going faster. It involves exponentially multiplying the amount of energy required. And as we approach the speed of light, the cost stops being large and becomes absurd. Imagine a spacecraft roughly the size of the International Space Station. To propel it to 50% of the speed of light, we would need more energy than all of humanity has produced in its combined history. Not the electricity of one country, not the energy of a century, our entire energy history. And that is just to accelerate. It doesn't include slowing down. It doesn't include protecting the crew. It doesn't include life support systems. But the real limit goes deeper. According to special relativity, the closer an object gets to the speed of light, the greater its effective mass becomes. It doesn't literally become infinite at rest, but from an energetic standpoint, the energy required to keep accelerating it tends toward infinity. In other words, we can never reach the speed of light because we would need infinite energy to take that final step. It isn't a problem of materials, it isn't a problem of engines, it is a structural law of the universe. We can improve technologies, we can optimize fuels, but we cannot negotiate with a physical equation that defines how reality works. Before even thinking about intergalactic travel, we have already hit an invisible wall that says speed has a price, and that price grows until it becomes impossible.
Let's suppose something even more extreme. Imagine we achieve the unthinkable, a spacecraft capable of traveling at 90% of the speed of light. We have mastered the energy. We have built nearly perfect materials. Systems do not fail, nothing breaks. And yet, a problem appears that is not technical. It is existential. Time stops behaving as we expect. According to special relativity, the faster an object moves, the slower time passes for it compared to those who remain at relative rest. This phenomenon is called time dilation, and it is not a speculative theory. It has been measured with atomic clocks and satellites. For the crew, a journey might feel like 20 or 30 years. For Earth, centuries or millennia might have passed. And the greater the distance, the greater the difference. A journey perceived by astronauts as 200 subjective years could be equivalent to millions of years on Earth. Upon returning, if returning were even possible, they would not find their language, their culture, or their civilization. They would find a planet transformed by evolution, catastrophes, or even the disappearance of humanity. The journey stops being exploration, it becomes an irreversible exile. And communication doesn't remain intact either. Radio signals weaken with distance, and furthermore suffer from relativistic redshift. Their frequency is stretched until they become practically undetectable. A message could take centuries to arrive, and when it did, it would be distorted noise, incomprehensible to any future receiver. There would be no real-time dialogue, no coordination, no meaningful goodbyes. Even if we solve speed and energy, the intergalactic traveler would not be an explorer who returns with stories. They would be a castaway in time, disconnected not only by millions of miles, but by entire eras of history moving forward without them. In that scenario, leaving the galaxy is not an adventure. It is accepting that every link to your origin is broken forever.
Up until now, we have talked about distance, energy, and human time.
But there is a factor even greater than all of them combined. The universe itself is expanding. It's not that galaxies are flying through space like projectiles. It's that the space between them is stretching constantly in every direction, as if the very fabric of reality were dilating second by second. Imagine dots drawn on a balloon. When you inflate the balloon, the dots don't move across the surface, yet they move away from each other. That is what is happening on a cosmic scale. For a long time, it was believed that this expansion would slow down over billions of years due to gravity. But at the end of the 20th century, we discovered something unsettling. The expansion is not slowing down, it is accelerating. Something, what we now call dark energy, is pushing the universe outward. We don't know exactly what it is. We only know that its effect dominates most of the energy content of the cosmos, and that its effect is irreversible on a human scale. This introduces a deeply counterintuitive idea. Even if we built a perfect spacecraft, even if we traveled for millions of years, the destination could be moving away at the same time. It's like running on a treadmill that speeds up a little more every second. And even if you increase your pace, the treadmill keeps pulling ahead. There is a distance beyond which galaxies are moving away from us faster than light. Not because they violate relativity, but because it is space itself that is expanding. And relativity only limits what can move through space, not the speed at which space can stretch. Beyond that limit, no spacecraft, no matter how advanced, could ever reach them. Today, we know something even more shocking. Most visible galaxies are already unreachable. We can see their light because it was emitted when the universe was younger, when they were closer. But in their current position, they are already outside our physical future. It is a haunting visual paradox. We look at the sky and see objects that in reality are already gone forever. Every year, billions of galaxies cross that invisible horizon. They don't disappear, they simply move away faster than any signal or spacecraft could ever close the gap. Even if humanity developed unimaginable technologies, even if we overcame every energetic, biological, and temporal obstacle, we would still be confined within a limited region of the cosmos. Not for lack of ingenuity, but because the universe has a dynamic geometry that does not stop for our curiosity. We aren't simply far from other galaxies, we're in a race against a moving horizon, and with every passing second, that horizon moves a little further away, not because we travel slowly, but because the universe itself is widening the distance.
Let's suppose, once again, that we solve all of the above: the distance, the energy, the time, the expansion. There would still remain an obstacle that is not technological, it is biological. Our bodies are not designed for the deep vacuum, not even for near space, and much less for intergalactic space where practically nothing exists to protect us. Cosmic radiation is the first enemy, high-energy particles that pierce through tissues and materials as if they were air. On long journeys, this radiation would not only increase the risk of cancer, it could destroy bone marrow, alter the nervous system, and damage DNA in a cumulative and irreversible way. Shielding a spacecraft completely would mean adding tons of mass, and more mass means more energy to move it. We are back at the same wall. Then there's the problem of hibernation, a popular idea in science fiction, but in real biology, freezing a complex organism is extremely difficult. The water inside the cells forms ice crystals that rupture membranes and internal structures. Today, we can preserve tissues or embryos for a certain amount of time, but not entire human beings without causing severe damage. And if we rule out hibernation, another option arises: generation ships. Floating cities where several generations would be born, live, and die without ever seeing a real planet. Here the problem is no longer just medical, but genetic, social, and psychological. Maintaining sufficient genetic diversity over centuries is complicated. Avoiding hereditary diseases requires large and controlled populations, and sustaining a functional culture in a closed environment for millennia is something we have never achieved, even in much shorter historical periods. Furthermore, there is the human mind. We need horizons, open skies, natural references. Locking entire generations into an artificial environment could provoke profound psychological crises, a loss of purpose, or internal conflicts that are difficult to manage. Intergalactic travel would not be a heroic expedition. It would be an extreme experiment in human survival under conditions for which we did not evolve. Before physics stops us, our own bodies are already telling us something clear. We were not designed to cross the vacuum between galaxies.
When physical reality begins to close doors, imagination opens shortcuts. Warp drives, wormholes, space folds, portals. They are fascinating ideas. And what's most interesting is that they weren't born solely out of fiction. They were born from real equations. The so-called warp drive, theoretically proposed by Miguel Alcubierre in the 1990s, describes a mathematical way to compress space in front of a spacecraft and expand it behind it. In theory, the ship would not move faster than light inside its bubble. It would be space itself that moves. It sounds promising, but there is a devastating problem. To function, it would require negative energy in quantities equivalent to the mass of a planet like Jupiter. We aren't talking about a source that is just difficult to find. We are talking about a type of energy that we do not know how to produce, store, or control in physical reality. Furthermore, certain models suggest that such a drive could generate time paradoxes, creating situations where the effect precedes the cause. In other words, it wouldn't just break the speed limit, it would break the logic of time. Then there are wormholes, hypothetical tunnels that would connect two distant points in space. Another idea with a solid mathematical foundation in general relativity. But in practice, the wormholes we could form, if we even could, would be microscopic, unstable, and subjected to tidal forces capable of tearing apart any object that tried to cross them. Keeping one open would require, once again, forms of exotic matter that today belong to the realm of theoretical speculation. It's not that these ideas are forbidden, it's that they are beyond our current physical reach, and, according to many models, they might be beyond the reach of any civilization based on the matter we know. Science fiction offers narrative doors. Physics offers equations. And for now, the equations say something very clear. These shortcuts are not practical solutions. They are mathematical curiosities that have not proven to be feasible. We are not facing difficult technology. We are facing concepts that, today, are closer to what is mathematically imaginable than to what is physically buildable.
After traveling through impossible distances, unreachable energies, time paradoxes, and biological barriers, the initial idea becomes clearer. It's not that leaving the Milky Way is difficult. It's that, based on our current understanding of physics, it is likely not possible. And, paradoxically, that doesn't have to be a tragedy. Our galaxy contains around 400 billion stars. It is estimated that there could be tens of billions of potentially habitable worlds orbiting them, more planets than we could ever visit, even if we lived through millions of generations. We are not locked in a small room. We are inside a gigantic cosmic city. The intergalactic fantasy is born from our need for infinite expansion, but reality offers us something different, a territory so vast that no civilization could ever exhaust it. Accepting limits is not a surrender, it is maturing as a species. It means understanding that we don't need every galaxy to have a purpose, that we don't need to conquer the universe to be a part of it. And it also implies something deeper. If this is our only real neighborhood, then our planet is not replaceable. There are no nearby copies. There are no second chances on a human scale. The Milky Way is not a prison. It is an immense home, an ocean of stars where we haven't yet explored even a tiny fraction, a space large enough for millions of years of discoveries, cultures, and possible futures. Perhaps we will never cross the vacuum between galaxies, but within our own, we have more universe than any civilization could ever traverse. And understanding that doesn't reduce the wonder, it makes it more real. Accepting that we might never leave the Milky Way does not diminish our place in the universe, it redefines it. We are not a trapped species. We are a species living in a galaxy so vast that it could sustain exploration, discovery, and evolution for millions of years. And perhaps that is the true lesson. We don't need to escape the cosmos. We need to understand and care for it from where we are. This has been Impossible Horizon. If you are interested in continuing to explore the mysteries of the universe with calm, curiosity, and critical thinking, subscribe and join us on our next journey. Because the more we look at the sky, the more we understand that it's not about going further, but about better understanding where we are.